Okay, so let me take attendance first. Okay, Abdullah here? No. Oh,
Yes.
yeah. Okay. Kenya. Forastia, yeah. Queenie,
Yes.
Izar,
Yes.
yeah. Haris,
Yes.
Haris, yeah. Hold on. Shinke, Sheke, right? Sheke Nodia. Okay, Praveen,
Yes.
Marwan, Nodia. Okay, Shinho,
Yes.
Shinho, yeah. Yon,
Yes.
yeah. So, okay. Shaike, yeah. Shaike Nodia. Okay, it's 3, 6, 8. Okay, so Shaike not here. Shaike not here. Shaike not here. Marwan not here. Shaike and Marwan lah. Okay. Yeah, so let's continue. Okay, I believe you did the homework, right? So I asked you to do the last from page E onwards. Okay. The answer is given at the back. So any problem with the question? First, question 1. Okay, so answer is already given there. Does anyone have any problem with this structure question? No question. Okay, first, state what instrument should be used to measure the diameter of the wire. The micrometer screw gauge. Shaky, yeah. Okay, so your micrometer screw gauge. And check so as to avoid the systematic error. How do you avoid systematic error? Check the zero error, right? Check the zero error and subtract the zero error with the reading obtained. Okay. Oh, everyone is here. Good. Okay. Next, use so as to reduce the random error. Next is how do you reduce the random error? So, yeah, to take diameter at a different location. Okay, take diameter at a different location and obtain the average. Okay, repeat the reading at different location and obtain the average. Random error. Random error can be minimized by taking average. Okay. Okay, next, this one. Okay. So a digital voltmeter of 3 digital displays used to measure the potential difference across a resistor. The meter state that the accuracy is 1%, plus minus 1 digit. The reading on the voltmeter is 2.05 volt. For this reading, calculate the nearest digit. A change of 1% in the voltmeter reading. Okay, how do you do this question? Displays used to measure the potential difference across it. The manufacturer of the state accuracy is 1% and plus minus 1 digit. The reading on the voltmeter is 2.05 volt. For the reading, calculate the nearest digit. A nearest digit, a change of 1% of the voltmeter reading. Okay, so what is the answer should be for the first one? how do you do this? Okay, this question something different than what we did before. Why it's different? It has two type of error. It has random error and it has a systematic error. Positive 1% is the two random errors actually. Plus minus one digit also like random error. Okay, so the plus minus one digit you have to deal. You have to what do you call treat it later. Okay, first for this reading, calculate the nearest digit. The change of 1% the voltmeter reading. So what is the change in 1% of this voltmeter reading? So 2.05 times 0.01. So anyone, what do you got?
0.
0,
0.
0, 2, 5.
0.0205. But you must go for one significant figure, so 0.02. 0.02. Okay. So then next, maximum possible value for the potential difference across the resistor. So how do you do this? So the answer should be 2.05 plus minus 0.02. Okay. But one digit plus minus one digit, so it should be 0.03. It becomes 0.03. Sorry, anyone? Oh, not admitted. Okay, so I think what's the answer given for the second one? 0.03. Anyone?
Zero point zero two.
0.02. Question right. Sorry. 1% is 0.02. Yeah, the maximum value is 2.08. Okay. Understand why they got 2.08? Why they got 2.08? Okay, why they give more 2.08? Sorry.
Yeah.
Okay. Yeah.
Yeah.
The question.
Sorry for entering late. Zoom had a problem not letting me in.
Okay then. Okay. Okay. So the maximum possible value should be 0.02, but because they said one digit plus minus, that means maximum error going to be 0.03. So 2.05 is going to be plus minus 0.03, the final answer. So because they're asking what is the maximum possible value could be is 2.08, 2.05 plus 0.03, 2.08 should be the answer. That's why they give 2.08. Okay, B, the reading of the voltmeter has high precision. State and explain why the reading may not be accurate. Of course, highly precise means it has a precision is affected by random error or systematic error. Precision? Yeah, it's affected by random error, right? So the voltmeter has very high precision. In this case, means high precision means it has a lot of digits at the back. Okay, maybe three decimal places. So high precise lah. But still explain why the reading may not be accurate. So is it a digital one or is it a digital one? But digital means the reading at the last digit, the last digit on the right, the first digit on the right might fluctuate. Okay, fluctuation can happen. It might have zero error, and I can't say zero error. Fluctuation mainly causes the reading not accurate. Sorry, fluctuation is random error. Systematic error. Okay, it might have a systematic error. Blame to the systematic error. So it should have a zero error. Systematic error, which makes all the reading to be one-sided. Okay, shifted to it's one-sided and fixed pattern. Okay, So you have to blame a systematic error, not random error. Okay. Okay, next, then any other questions you have? Done, eh?
Number 5.
Number 5. Which page is that? 31.
33.
33, yeah, okay, 33. Okay, 33, number 5. Okay, this question. Answer it again, everyone. Quantity x to be determined from the equation. X is p minus q. P is value given, q is value given. What is the percentage answer for the x to one significant figure? They want, they want changes of x over x, or changes of x over x times 100%. They want changes of x over x times 100%, right? What do you call? The percentage answer in the x to one significant figure. So you write the, need to annotate. Okay, all done. So changes of x will be what? Hold on. So of course, you are looking for changes of x over x times 100%. Of course, okay, you're looking for this. So you need to find changes of x first. Changes of x is what? Changes of p plus changes of
Q.
q. Yeah, changes of q. So find the changes of x first. So what is the changes of x? Changes of p plus changes of q. Okay, I hope you have the question with you. I can't see the question. Changes of p how much?
0.03.
0.03, yeah? 0.03, yeah. Okay, plus changes of q. Changes of q is?
The total is 0.0.
Total is 0.03. Okay. So yeah, total is 0.03. So yeah, then you find your x. X is what? P minus q.
0.44.
The final is 0.44. Okay, that's it. Changes of x. So put here, you can get the answer, right? 0.03. Okay. Okay. Any other questions? You don't have? Then today's lesson is going to be like again, kind of like. Yeah.
Can you talk about the cathode ray one?
Cathode ray oscilloscope.
This one.
Which question?
Number 5. This one.
Number 5. Oh, this one.
Yeah.
Okay. Okay, everyone. Let's see. It's November 10, paper 11, page 32 question. Okay. So this question is a little. You need to use a little logic. Okay. So 1 minute for those who haven't tried. Read the question. Try to have some idea. The diagram shows a cathode ray oscilloscope. So the flywheel is rotating. Each time the magnet passes the coil, a voltage pulse is generated, which is passed to the CRO. The display of CRO is 10 centimeter wide. So we've got 10 centimeter range of scale. The flywheel is rotating at 3,000 revolution per minute. Then it makes 3, like your car RPM, right? It's like RPM. The car, you see the speedometer, you can see one scale for RPM, revolution per minute. That means the thing is rotated 3,000 times in a second, in a minute. So which time-based setting will display clearly separate pulses on the screen? Okay, they're asking which is the best setting for us to analyze the pulse. To analyze the pulse means to find the period of the pulse and everything. Okay, tell me on the screen, how many pulse do you want it to appear? How many pulse? Is it 100 or is it within 10 or 1 or 2? I think around less than 5 is enough. Because we're going to analyze pulse means less than 5 is enough to analyze the period, height, amplitude, and everything. We don't want to have too much. We don't want to have too little. Okay. So which scale is the best? So how do you need to calculate what? You need to calculate the period of one pass first. What is the time taken for one pass? What is the period of one pass? That's you have to calculate first. Do you calculate the period of one pass? 3,000 rounds per minute. That means it gives 3,000 pulse in a minute. Okay. That means what is the period of one pulse?
2.02.
2.02.
2.02.
Okay. Go to the whiteboard to clear it. So 60 seconds divided by 3,000 lah. You get the period, right? You get a period. Period. So how much you get? Again,
0.02.
0.02 seconds. So 0.02 seconds. That means one pulse to another pulse. Okay, the duration from the center to center, we can go for 0.02 seconds. Okay, on the screen, we don't want to have like this. We don't want to have like 100. We don't want 100. If its answer is going to be very close, so we can't read the period very well. Maybe 4 to 5. So which scale is the best? So go back to the scale. Cannot trace. If it's 1 second per centimeter, 1 second per centimeter is 1 second. That means within 1 centimeter, how many pulse will appear? 1 second. 1 second in 1 centimeter. So how do you know how many pulse will appear?
80.
Yeah, 80.
80.
So 1 second you divide by 1 second, you divide by 0.02, right? So you get how much? You get 50.
50.
Yeah. So only in 1 centimeter of interval, you're going to see 50 pulse. Is it good or bad? It's not very not difficult for us to read the reading. It's because the pulse are quite close. So A is definitely not the answer. So A, I don't think so. 50 pulse in a centimeter. B, how many pulse in a centimeter? 10 millisecond divided by 0.02 seconds. Actually, it's 20 milliseconds, right? 0.02. So how much? B, how many pulse happen in 1 centimeter? Half, right? Yeah, half. 10 millisecond divided by 20 millisecond. 20 millisecond is 0.02, right? So it's half. 0.5 pulse. This looks good. That means in 1 centimeter, you only going to give 0.5 pulse. That means 1 pulse going to take 2 centimeter. 1 pulse is 2 centimeter. I think within 10 centimeter, you're going to see 5 pulse. Okay, this is good. This is good. Okay, 5 pulse is very good to read the period. Okay, I think B better than A, of course. How about C? 100 microsecond. 100 microsecond divided by 20 millisecond. I don't think so. How much you get? 100 microsecond divided by 20 millisecond. 20 millisecond. Both change to the same unit. 100 millisecond is how many millisecond? How many 100 microsecond? 0.1 millisecond, right? 0.1 millisecond divided by 20 millisecond. It's very little. So for C, for 10 centimeter, you can't even see one full cycle, I think you might see 20 or 30% of the cycle. So you can't measure the period. C is totally out. Okay. D even worse. So the answer is B. Okay. So again, what you need to understand in CRO, do you need lots of oscillation or little oscillation? Just 4 to 5 is good. Okay. So you have to check which scale gives you around 4 to 5, less than 10 number of oscillation. That's what you need to choose. Cannot be too little. Too little means cannot be like less than 1. Cannot be more than 10. 100 all are quite a lot. Okay. So therefore we go for B. Okay, make sense? Anyone have still confused? Okay, Can, Okay, any other questions? Those who maybe hard work enough, maybe you did other question than the one I asked you to do. Because we're going to wrap up with this topic.
November 2009,
November
P22.
November 2009. November 2009.
C.
Which one? Part C. Okay, this one. Okay, the value of L and T. Okay. So let's be. Good question. Okay. For this, maybe some of your friend haven't tried yet. Let me go from the beginning, This question we go from the beginning. Try to get some idea what you're going to do. I think you need to go for part. Okay, a simple pendulum may be free fall G. The measurement of made L and T given. Calculate the period for T. Calculate the percentage uncertainty for the T. So changes of T over T is equals to equation given. Oh, so no. The data already given one. So T is what? 0.03 divided by 1.93 times 100%. You get the answer here. Percentage, right? 1 or 2 SF. And L also same thing. 1 over 92 times 100. You get the percentage here. Okay, so T and L percentage we got. Okay, now they give the equation. They're asking to calculate the G. What is the percentage uncertainty for the G? We did many equations. So what is the formula? Anyone? Okay. Changes of G over G equals to changes of L over
Changes
L.
of
L plus.
plus 2 changes of T over T.
Okay, then you get times 100% both sides. So you get the G value. Okay, now come to C. Okay, everyone. The value of L and T are used to calculate the value of G as 9.751. Okay, actual reading is 9.81, but here the student did an experiment. We can't expect him to got 9.81. It can vary because got error. So this fellow got 9.751, but he wrote 9.751. He wrote 3 decimal places. Okay, so they're asking, by reference to the measurement in L and T you got above, suggests why it would not be correct to quote the value as 9.751. That means what they are trying to ask is, what is the reason he can't write 3 decimal places? Why he can't write 3 decimal places? That's the question here. Why he can't write the decimal place he's going to portray? It depends to what factor? The error, right?
Yes.
We have to check error how many decimal places, right? If error 2 decimal place, the final answer 2 decimal place. So the values depend to the error decimal places. So how much the decimal place for the error you get? That you have to check. How much is the error? It depends to the answer here. What is the gravity percentage uncertainty? Anyone?
4.19.
4.19. 4.19. Okay, let me go to the paper. Okay, so I need your feedback. Okay. So the percentage error for the G is how much? 4.19%. 4.19%. The student got how much? 9.715, right?
5.1.
5.1. Okay, the error is plus minus 4.19%, right? Okay, so 4.19% of this is how much? Give me the value. 0.04 times this. What do you get?
.41.
0.41. Okay. Now you know the reason already, right? Okay. So what's the reason? Because the uncertainty is 0.4. How many dp? It's 1 dp. Okay. Therefore, your error, your value must go for 1 dp. So you're supposed to write 9.8. You should not write 9.75. You should write 9.8 because the dp must be, both dp must be same, right? That's the reason. So the blame you say is what? Because the uncertainty of 4.19% out of 9.751 is 0.4 for 1 dp. That because it's 1 dp. Therefore, the final answer must be 1 dp. So you should write 9.8. Okay. So that's the reason you have to give. A good idea? Yeah. So what you have to say? You say because 4.19%, the actual uncertainty of the gravity is 0.4, which is 1 dp. Therefore, the actual value also must be 1 dp. So therefore, can't write 9.751, which is 3 dp. Okay.
Okay, thank you.
Okay. Any other questions? Good. I'm happy that you are trying other questions. Any others? Have any other questions? If you don't have questions, then I select because today's
Sir, November 2002,
November
number 2,
November 2002. Or
number 2C.
yeah. November 2002. Yeah, 2002. What is this? Which number? C.
2C,
2C.
the structure part.
Yeah, this one. This is the question I want to ask you. Okay, class. This is worth doing. Everyone, let's we do together. Those who haven't tried, let's we try together. Okay, question 2. This is a little different from the others. I can say this is the only one different from the others. One of its kind is in this paper. You give a try. Okay, first part A. 1 minute for you. The length are recorded before stretching is L0. After stretching is LS. Okay. They are asking for the change in length, LS minus L0, quoting your answer with its uncertainty. So what's the answer will be? With its uncertainty. So changes how much? LS minus L0, 1.6, right? 51.6 minus 50. Answer will be what? 1.6 plus minus how much? Anyone?
0.2.
Yes, it's going to be 0.2 lah. LS plus L0 one. Okay, beginning is always easy. So 1.6 plus minus 0.2 answer. Okay, you scroll down. Okay, now B, find the fractional change in length. LS minus L0 over L0. So anyone? It's also quite easy. So LS minus L0, we know here is 1.6. Over L0, anyone? What's the answer? 1.6 divided by L0. 1.6 divided by L0, 50. So 1.6 divided by 50, what do you get? That's the answer should be here. Okay. Fractional change. Follow the least significant figure. So I think you go for 3 SF lah, the answer. Okay, anyone got the answer? This one?
0.032.
Okay, hold on. Yeah, hold on. 0.032. LS minus L0 over L0. Okay, so 0.032. Okay, so now the next question is the challenging one, not the tricky one. Next, they want, this is the last part. Find the uncertainty, answer B. Find the actual uncertainty of the answer B. They're asking, what is the uncertainty for this? Okay, why this is unique? We never seen before. Why this equation is unique? Because two different worlds together, minus and divide together. Minus plus is one group normally. Yeah, uncertainty formula is the same. Divide and times is one group. Divide and times together we can deal. plus and minus together we can deal, but minus and divide, two different worlds join up together. So how are we going to solve this? Okay, so what you have to do like this. So you put this as, assume this as y. Okay, we put, this is the formula. This is the formula. So we know y, this is your y like that. This is your y. You are looking for changes in y, correct? You are looking for changes in y. This is the question. Okay. So we need to kill the existence of both together. The ls over l naught, we pack them as one single number. So we rewrite the formula. So y equals to, I put L naught. I don't want the minus to be placed here. So ls over L naught, I take it as x. I put a symbol x is what? X, I take it as ls minus L naught. Okay. So therefore, what is the ls value, x value? You learn, you calculated earlier, 1.6. How much? Plus minus 0.02. 0.02, right?
0.2.
0.2.
Oh, sorry, 0.2. So 0.2. Okay, this is your x. So here you just put x. Now it looks good because only divide. But the minus we already solved it into a one single digit. So you have to do this. So now you're looking for changes of y. So how do you write the uncertainty formula? Changes of y over y equals to what? Changes of x over x plus changes of L naught over L naught. This is what you should do. Now you can put the values. Changes of x over x is 0.2 over what? 1.6 plus changes of L naught. You're reading on top. L naught is how much? 50. 50, right? Changes of L naught is 0.1, is it? 0.1. Y, what is the value of y? 0.032, right? You can find the changes of y. So you can work out the changes of y. What's the answer you got? Anyone? These are changes of y. So anyone got the answer? Okay, so what I'm trying to tell you here, if two worlds together, minus divide together, the minus, you have to solve it first. Okay, you have to solve it first. Make it as a x equals to ls minus L naught. Get a single number for them. What is x stands for with the value and with its uncertainty. Then immediately kill the minus. Just put a single symbol x. You go any symbol can it's x. A little relief because it's only divide, so you can solve. Okay. So what's the final answer? Anyone? 0.2, 1.6, 0.1, 50. The 0.032 you have to minus, you have to times with the right. Anyone? Okay, I hope you get the idea. Can understand? No problem, eh? Who asked this question? So you understand this okay? You still got any?
Yes.
Can, eh? Okay then. Okay, so we go to the any other questions? Any other questions? So measurement technique, you can, eh? Okay. Okay, so we have about 15 minutes. So let me ask more questions. Okay. Okay, this question 4. Remember 4, question 4. Okay, this one. Read first. The deflection needle of an ammeter was varying like that. Which diagram could represent the appearance of the scale of this meter? me.
A.
Yeah, it's better. Okay, pitch meter. The needle, the meter is sensitive at a low current or high current?
Low.
At low current, very good. The needle is quite sensitive at low current. How? How do you know low current? Because at a low current, the deflection is lot, the gradient is very high compared to later. So gradient at the beginning is very high. That means a small change in the current, the deflection is big. The deflection is big. So sensitive at the bottom. A small current change, the deflection is big. The needle going to turn a lot. It then become less sensitive later. Less sensitive means for greater current, the deflection is become very small. That means the scale must be quite close to each other. So which is the answer? Anyone?
A.
Should be A. Should be A. Very sensitive at a low current. See, the very wide means very sensitive, very sensitive. And towards the end, it's less sensitive. The needle less sensitive. We never deflect that much. So this is how the graph looks like. Okay. Can you draw for me how the graph looks like for B, C, and D? Let's go for B first. Anyone can sketch for me the graph? Okay. Can you annotate? Can you share your drawing on this? Anyone? Do you allow to annotate? Did I allow you to annotate? I don't know. Anyone able to write? Can you draw for me the graph here? How the graph going to looks like for this scale? Is sensitive at the beginning or sensitive later? The deflection is greater later, right? Because the separation is big. So how the graph looks like, deflection versus current? Anyone? So how is it should be? It's sensitive later. Big current is sensitive. Sensitive means what? The angle of deflection should be big. At the beginning, so it should be like this one going up. For a small current, the deflection is very small. Very small. But for a big current, for the same amount of change, the deflection is big. See, the deflection is big. Big change. So very sensitive. So B should be going up. Okay. So how about C? Okay, C. How the graph going to looks like? You just tell me the gradient. The gradient at the beginning. Beginning sensitive or not? Beginning gradient going to be greater or smaller? Higher or smaller? The gradient. The gradient going to be higher. Then the gradient going to be less sensitive. So gradient going to be lower. Then here the gradient going to increase again. Big deflection one. Here all big deflection. Here very little deflection. So less sensitive. The needle not less sensitive. So how the graph going to look like for the C? So greater gradient, less gradient, and greater gradient again. So this is how the graph looks like for C. Okay, sensitive, less sensitive, more sensitive. Okay. So how about D? D at the beginning going to be less sensitive, more sensitive, then less sensitive. So how the graph looks like? So at the beginning was less sensitive, so less gradient or more gradient? Less gradient, then more gradient, then less gradient. This is how the graph looks like, sensitivity. Okay. Okay. So I hope you following. Okay, this is the sensitivity part. Eh? Okay, this one, 6. What's the answer? Which student obtained a set of results that could be described as precise but not accurate? Which data looks quite precise but not accurate?
Okay.
So which one is very precise? Precise but not accurate.
Donkey.
Donkey, yeah, good.
D.
D, yeah. If some of you, if after your degree, after your A levels, go for degree after that, maybe you go for masters or PhD. I think you need to analyze data, so you check the precisions of the data and the accuracy. So you have to learn that. Which is accurate and precise? Which data is accurate and also precise? A, B, C, D.
Boy.
Boy, accurate and precise.
A.
Isn't A?
A.
A look more accurate, right? A is accurate and precise. A is accurate. How what you can tell about B? Is it accurate? Is it precise?
No.
Is it accurate?
No.
Okay. When we categorize as accurate, if at least one reading hit the target, we say it is accurate. So B, the first reading was 9.81, it hit the target. So you said B is accurate. At least once he got the value lah. So you said it's accurate, but it's not precise. Not always hit the target. Only once it hit the target. So it's accurate. Okay. So B is accurate, but not precise. Okay. C, what you can tell about C? Of course, not accurate and not precise. C is the worst reading. Okay, good. Okay, I think we've done most of the questions already about kinematic, about this topic, measurement techniques. So this is next slide. We're going to go through very fast. Okay, you're going to wrap up this topic. I want you to have a feedback from you. More faster you give, more faster I can finish the class. Okay. Okay. So this is another file which you need to fill up. Okay. Tell me for ruler, what is the precision value?
0.0.
0.01.
0.1 or 0.05?
0.05.
0.1.
5.
0.05. The precision. Precision means half of the smaller scale lah. But if you read the length, 2 places uncertain, it becomes 0.1 lah. That's uncertainty. Precision of the instrument is 0.05. When we can Vernier caliper? Yeah, sorry. 0. Okay, sorry, I made a mistake. Ruler better go for like 0.1. This is 0.01. This is 0.03. Mass here, digital. What is the precision?
0.01.
0.01. Okay, this looks quite small. Okay, we skip this. Okay, this one. What is the precision? Voltmeter?
0.1.
0.1. Good. Half of the smaller scale. Okay. What is the precision? What is the precision? Mercury in glass?
0.05.
0.05. Smaller scale is 1, right?
0.5.
0.5. Good. 0.5. Okay, stopwatch. Okay, stopwatch. 0.01 can, 0.1 also can. But what I prefer, 0.1. Go for 0.1 lah. 0.01 also accepted. I think I told you the story. Why you can't go for 0.01? Not logical to go for 0.01. But they accept it also, Cambridge, because of your reaction time, quite big. So we go for 0.1 lah, although it displays 0.01. Okay. Okay. So, hello. Okay, sorry, I think the internet got problem. Okay, listen, Okay, what is the one source of systematic error? Zero error and zero error lah. Systematic error is one type of zero error. Random error is can go for hello. Can you listen to me? I think something's wrong with the connection. Hello, can you listen? Everyone?